So welcome everyone. We were lucky these two last days to have these very nice pedagogical lectures, and now we switch to the more conference-like part of our conference, and we will start with, so we will alternate between some longer talks from invited speakers and shorter talks by contributed speakers. And we will start today with Magda Carr from Newcastle University, who will talk to us about shoaling internal solitary wave. So Magda, the floor is yours. I don't know if you prefer that if people have some questions, can they put the question, if they put questions in the chat, can I interrupt you to or you prefer to have the questions at the end?
Yeah, please do. I'm happy to be interrupted at any point, either through the chat or just by unmuting, whatever works best for people. No problem.
Okay. Well, the floor is yours, Magda.
Thank you, Philippe, and hello, everyone. I'd like to begin by thanking the organisers. It's a real pleasure to be involved in this workshop and to have the opportunity to talk to you all, and also thank you very much. Thank you to all the participants for joining in. So today I'm going to be talking about shoaling internal solitary waves, and this work has been done in collaboration with Samuel Harton-Evans, who's my PhD student in Newcastle University, with Marek Statsner from the University of Waterloo, Peter Davies from the University of Dundee, and Koen van der Waal from the Technical University of Eindhoven. So I'll start off with some background and motivation before going through the methodology. So we will approach this from both an experimental and numerical point of view, and I'll then present some results. So in the first part of the talk, I will present results for shoaling mode 1 internal solitary waves, and in particular, we'll be looking at the effect of stratification on the shoaling dynamics. And I'll then discuss shoaling mode 2 internal solitary waves, and we'll be looking at the fundamental physics of the fluids in that case. So solitary waves were first discovered by John Scott Russell in 1834 on the Edinburgh to Glasgow Union Canal. And Russell was watching a horse which was towing a barge. It came to an abrupt halt, and as it did so, it set a surface wave of elevation into motion, a bit like the one you see here in this recreation. So Russell followed this wave on horseback for several miles before he lost it in the windings of the canals. And what he observed was that this wave could travel a very large distance without any change of form. So he referred to this as a wave of translation. And he later showed that these waves have a speed which depends on their amplitude. So the bigger the wave is, the faster it travels. And he showed that if you collide two of these waves, either head on or through an overtaking experiment, then they just pass through one another without any change in form, except for a slight phase shift. So this is where the name solitary came from. They have this solitary type behavior. So today we're going to be talking about internal solitary waves. So these are solitary waves that travel along density interfaces within stably stratified fluids, and they owe their existence to an exact balance between nonlinear wave steepening and linear wave dispersion. And they occur in many geophysical settings wherever you have a stratified fluid, and we also get them in non-geophysical settings as well. I'm going to be focusing on oceanic internal solitary waves. So as I'm sure we all know, everyone on this call will know that the ocean is a stably stratified fluid. So typically the deep waters tend to be colder and saltier than the near surface waters, which tend to be warmer and fresher. So as a result, the near surface waters are less dense than the deep waters, which are more dense. And between these two water bodies, we have a region where the density changes relatively quickly with depth. I'm going to refer to that as the picnic line, and you can just think of that as being an interface between two fluids of different densities. That interface can act as a waveguide for internal wave motion. So we heard from Paul Linden earlier in the week that internal waves are very important in the oceans. They're important in the context of meridional overturning circulation. So we know that they're a source of momentum and mixing within our oceans. We also know from physical observations that they can transport heat and nutrients vertically. They can resuspend sedimentary material and also transport mass over very large distances. And these two beautiful observations you see here, I'll come back to later in my talk and explain them in a little bit more detail. But internal waves are of interest from a fundamental physical oceanographic perspective. They're also of interest to the offshore engineering community, who want to know what kind of impact loads they have on things like cables, rigs and risers. They can cause scour on pipelines, and they can also interfere with underwater communications, which is of concern to offshore engineers and also, of course, to the submariner community. Internal solitary waves have very different properties to surface waves. So typically they have wave speeds of the order 0.1 to 1 meter per second. They have wave fronts of the orders of tens to hundreds of kilometers, wavelengths 0.1 to 1 kilometer, and amplitudes of tens to hundreds of meters. And they typically travel in a rank ordered wave packet. So the leading wave has the largest amplitude because we have this relationship between amplitude and speed. So they self-order. The biggest one is the fastest. The second biggest is the second fastest, and so on. And if you're allowed to let a wave packet like this travel for an infinite amount of time, this leading wave would just get away from the tail. When I talk about amplitude, I mean this distance here, so the displacement of the picnic line to maximal extent. So in the South China Sea, they're routinely observed with amplitudes of 120 meters and fluid depths of just 340 meters. And the biggest recorded wave is this observation by Huang et al., again in the South China Sea, where there was an observation made of a wave with an amplitude of 240 meters. And just to put this in context, to give you an idea of scale, if we just want to have a look at this picture here, this is a photograph of the Bangalore skyline at night. So I was really disappointed not to get to Bangalore in person. So I felt obliged to put a photograph in and have a look at what Bangalore looks like. This is the UB Tower in Bangalore. It stands at 123 meters tall. So the UB Tower, the height of that tower is about the same as the amplitude of an internal wave in the South China Sea. So there really are big structures within our oceans. So as an internal wave disturbs the picnic line, it induces a current at the surface, and that gives regions of rough and slack water on the surface of the ocean. Okay, so it can affect the roughness. So we can look at this from space. So here I'm showing you 3 images from NASA's website. And we're looking at the surface of the ocean. And if you look carefully here, you can see these bands of light and dark. But what we're looking at here is the surface signature of internal wave motion. So the internal wave motion is going on subsurface. There's a current induced at the surface, which gives these regions of rough and slack water, which are being picked up with the satellite imagery. So using remote sensing and also in situ measurements, we're able to build up a picture of the global distribution of internal solitary waves. And here you can see that internal solitary waves are really widespread throughout the world's oceans. This picture also shows that we've got many observations in and around our coastlines and in and around the continental shelf and indeed the continental slope. So we expect internal waves to shoal, to interact with topography at the bed of the ocean. And indeed, here are a couple of observations of shoaling internal waves from the field. So this first one was made by Mohm et al. On the Oregon shelf. The black line you see here are lines of constant density. So these are isopycnals. And you can see that as this wave shoals, it's propagating from left to right, going up this topographic slope, that there's enhanced optical backscatter being measured near the bed. And Mohm et al. Say that this is due to resuspension of sedimentary material as a result of the internal wave shoaling. In this second image, this was made by Droghi et al. In 2016. And here we're looking at a SAR image. So we're looking down on the surface of the ocean. This is the Tyrrhenian Sea, just off the coast of Italy. And there's a surface signature of an internal wave field. And if we go along this transect AB, and have a look at the topography along transect AB, you can see that we've got a slope on the bed of the sea, and there's also some sand waves on that slope. And Droghi et al. Postulated that the formation of these sand waves was due to this internal wave shoaling on the slope. Okay, so we do have some field observations of shoaling. However, we don't have a really good understanding of the physics behind the flow. So this is where we come in from a modeling perspective. So we're going to approach this problem using experimental modeling and also numerical modeling. And let me just talk you through my experimental method first of all. So I've got a wave flume, which is 7 meters long. It's 0.4 meters wide and 0.6 meters deep. And we begin by stratifying the tank. So at the minute, you can see the tank is being filled with water. So beneath the tank, we have a large reservoir where we mix up salty brine solution. We then pump that into the tank. Okay, so this is the bottom layer. It's just homogeneous brine solution. We then have an array of sponges that we sit on top of the water column, and we very slowly drip feed fresher water from these feeder tanks that sit above the tank. So in this particular experiment, we're using something called the double bucket technique, which Patrice mentioned yesterday. So the way this works is, in this bucket here, we have fluid, which is salty, and it matches the density in the bottom water layer. In this second bucket, we have fresh fluid. Initially, these two are set up to be in hydrostatic balance. There's a valve between these two reservoirs, and as we drain from the salty one, we open the valve between the two. So as we drain from the salty reservoir, it gets diluted at a continuous rate from the fresh water, and hence we add a linearly stratified layer onto the top of our water column. We use these sponges so that we don't get a lot of mixing and the flow, and we fill very, very slowly. So once the tank is stratified, at the upstream end of the tank, we have a gate, which you can't actually see. So down here, there's a gate, and behind the gate, we fill with a volume of fresh fluid. So the fluid we put behind the gate matches the density at the top of the water column. So we end up with a density gradient across the gate, so that when you lift the gate out, the fresh fluid rises, the heavier fluid in the main section of the tank falls, and that creates a disturbance on the picnic plane, which propagates into the main section of the tank as an internal salty wave of depression. So in all the experimental movies you're going to see, the forcing is driven purely by buoyancy. There's no mechanical forcing, no input of energy of that way. It's all driven by density difference and buoyancy, essentially. Okay, so to measure the density field, we've got these conductivity probes that sit above the bed of the tank. They measure conductivity. When we drive them down through the fluid layer, the conductivity of the water changes with changes in salinity, and hence we're able to infer the density field. Beneath the tank, you can see there that we have a light sheet. So the base of the tank is transparent. And we have a light sheet which comes up in a thin sheet of light, and we view from the side. So we're going to be looking at a two-dimensional slice of the flow field. So to measure the flow, we seed the water column with neutrally buoyant light reflecting tracer particles and illuminate from below and view from the side. We use something called particle image velocimetry, which essentially uses a pattern matching technique to track where particles go from one frame in our experimental movie to the next, so we can get the displacement field. And because we know the time between images in a movie, we can get the velocity. And I've already described how we measure density using the conductivity sensors. So I want to show you a movie from the lab now. You're looking at this in a false color scheme. So if you saw this with the naked eye, you would just see white dots on a black background. So this is just a false color scheme that you're looking at. So this lower layer, which is heavily seeded with particles, is a salty layer. This region here where you see a congregation of particles is the picnic line. And in this particular experiment, we had a homogeneous layer on top. So this is not linearly stratified. This is just a homogeneous layer of fresh water. And you can see we have a flat bed here. And when I play this, I just want you to concentrate on the flow near the bed of the tank. So as the wave propagates from left to right, you can see that the fluid is accelerated in the negative x direction. It reaches a velocity maximum under the trough of the wave. And then as the wave goes past, the flow decelerates. And if you look carefully, you should be able to see this jet going along the bed of the tank in the same direction as the wave. So let's just have a think about what's going on here. So under the front part of the wave, we have that the flow is accelerated. So we have what's known as a favorable pressure gradient in the flow direction. Whereas under the rear half of the wave, the flow is decelerated in the negative x direction, and we have an adverse pressure gradient in the flow direction. If you have an adverse pressure gradient, you can get boundary layer separation. And we did some theoretical predictions as to where that boundary layer separation would occur. And we saw that there's good agreement with that theoretical prediction and the onset of this flow reversal. And obviously, if you have boundary layer separation, then by continuity of mass, you're going to get this reversal coming right along the bed of the tank, as we saw. So this was actually predicted in the late 90s by Hammond and Reddycop. And Larry Reddycop and Pete DMS's later said that because you have an inflection in the velocity profile at this point here, they showed numerically that you can also get an absolutely unstable global instability, which manifests itself as a roll-up of boundary layer vorticity. And they saw numerically that you got coherent vortices shed upward. So we went back into the laboratory to have a look at this. So in this lower movie, again, we're in the lab, we're zoomed right in on the bed now, and I'm increasing the Reynolds number of the flow. The movie you see at the top here is the corresponding PIV output. So you're going to see a load of velocity vectors. It's a little bit messy at the start as the wave goes past. So this is the wave just going past. And if you just concentrate on the flow near the bed, you can see as the wave goes past, there's the flow reversal going right along the bed of the tank. And if you look at the top of the flow reversal, you'll see where there's inflection in that velocity profile, we'll get these vortices forming. And they are resuspending particles off the bed and being shed upwards into the water column. And I must just quickly mention Priti Shivram. She was a visiting student from Perth in Australia who did a really good job helping out in the lab. So around the same time as that work, this beautiful field observation by Quaresma et al. On the Western Portuguese mid-shelf was published. Let me just explain what you're looking at here. So the color scheme at the top is temperature. So you can see the thermocline is being disturbed by an internal wave train. The color scheme at the bottom is eco-intensity. And you can see we have this strong signal at the bed of the ocean. And this is thought to be resuspension of sediment. Okay, so that was nice. That came out around the same time, showing that internal wave motion can indeed cause instability and turbulence in that bottom boundary layer. So everything I've presented so far has just been for a flat bed. And that's because I wanted you to just see what the flow features look like when the bed is flat and understand that we can have flow reversal because the boundary layer separates and the generation of vortices. I now want to discuss what happens in the shoaling case. So if we put a linear topographic slope at the bed, what do the dynamics look like? So there's already a lot of literature out there about shoaling internal solitary waves on a linear topographic slope. So Bruce Sutherland and others did some lab experiments on this and showed that you can classify these shoaling waves into different kinds of braking. So you can have no braking, surging, collapsing, and plunging. And Leon Bogman and others have classified this shoaling into different types based on something known as the internal Iribarren number. So this is just defined to be the slope steepness divided by the square root of the wave steepness. And Leon showed that you can get a qualitative change from plunging to collapsing to surging as the Iribarren number increases. And on gentle slopes, they saw fission followed by bolus formation. And they've recently shown that you can improve delineation if the Reynolds number is considered. Okay, so we know a lot. However, all of these past studies have focused on one stratification only. So they've concentrated on a stratification where you have homogeneous fluid in the bottom and top layers separated by a relatively sharp or thin pycnocline.
May I just ask you how you spell Iribarren?
So how you spell it?
How you spell it, because you didn't write it in the...
Yeah, so it's, let me see, it's I-R, I don't know if it's double R, A-B-B-E-N.
Okay, Iribarren. Okay.
So I think it's I-R-A-B-B-E-N, if I've not made a mistake.
Okay,
So there is a surface equivalent. So if you look in the surface wave literature, this is where the Iribarren number was first defined, and it was slope steepness divided by wave steepness, and this is the internal wave equivalent.
Okay. Thanks.
Thank you, Philippe.
Maybe I use the interruption to mention that when you show movies, for some reason, they don't really play continuously. We only see images every few seconds. So
okay.
If you want us to see something specific on a movie, you probably might want to stop the movie at this moment for you.
Right. I will do that. And I will also, let me just stop the share so I can, I'll switch my own video off as well and see if that helps. Okay, thank you, Philippe.
There is a question while we are at it from Adele, who asked, what do you mean by Reynolds number improve the delineation?
Okay, so good question. So I'll show you some plots in a minute, some classification plots where you have different regions in parameter space to classify whether you have plunging, collapsing, surging, etc., etc. And in this recent paper by Nakayama et al., they said if you actually look at the Reynolds number as well, then you can get those regions better defined. Okay, so if you take Reynolds number considerations into your classification plots, you can essentially make the boundaries between these different things sharper, and you can get a more accurate idea of what's going on in parameter space. I think were there some more questions in the chat, Philippe? Okay, so I just want to quickly talk a bit then about stratification in the ocean. So I said past studies have concentrated on a stratification that looks essentially like this. So homogeneous layers top and bottom and a relatively thin pycnocline. So something that would be representative of, say, the Labrador Sea. However, we know that in the ocean, stratification changes with location. So in the South Atlantic, the pycnocline is much more diffuse than in the Labrador Sea. In the Arabian Sea, it's more diffuse again. And in the East China Sea, we've got a stratification that essentially looks as if the water column is linearly stratified from top to bottom. So we thought it would be interesting to look at the effect of stratification form on shoaling and see if indeed that made any difference to the dynamics. So we complemented the experimental study with some numerical modeling. And the method we've used is called SPINS. So this stands for a spectral parallel incompressible Navier-Stokes solver. So the first equation you see there is the Navier-Stokes equation under Boussinesq approximation, and it just represents conservation of momentum. So again, Paul talked about these equations earlier in the week. The second equation you see is for incompressibility, and the third is for the density field. So we just have the material derivative of density is equal to the diffusion. We impose no slip boundary conditions at the top and bottom of the domain, and we have free slip at the end walls to avoid doubly clustered grids. So this model has been developed by Kevin Lamb and Marek Statzner in Waterloo over the last 20 years or so. Okay, so here are the stratifications we're going to look at. So the first stratification we're going to consider is the one that people have looked at in past studies, and we only did this numerically, and we did this as a way of testing our numerical method. So we wanted to test our numerical method against what was already out there in the literature. So if I refer to a stratification as being a thin pycnocline or a thin Tange profile, we have homogeneous fluids in the top and bottom of the water column and a thin pycnocline separating them. We've also considered a stratification like the one you see here. I'm going to refer to this as the surface stratification, and we've looked at this both in the lab and numerically. So in this case, we have a homogeneous fluid in the bottom, and then a linearly stratified water column all the way to the surface. And finally, we'll also consider what I'll refer to as a broad stratification, where we have this very diffuse pycnocline, and we've just looked at this numerically. So here's the model arrangement. So we're going to have a linear topographic slope at the downstream end of the tank, and at the upstream end of the tank, we have this gate that I mentioned, and behind the gate, we put this generating volume of fluid, which has density ρ1, where this density matches the fluid in the top of the water column. And we use the same arrangement both in the lab and also in the numerical modeling. So this is our initial setup. So here's the classification diagram, and I will show you results from this in just a second, but I just want to give you the broad picture at the start. So I'm plotting slope steepness against wave steepness, and the different colored data points correspond to different kinds of shoaling. So blue is fission, green is plunging, yellow is collapsing, red is surging, and these gray ones are unstable surging. If we look at this first panel, first of all, this is for the thin Tange profile. So this is where we've got something we can compare against in the literature. So plus signs and cross signs are from previous investigations that have been both numerical and laboratory based. And filled circles are our numerics. So the circles here are our new investigation. And you can see that we've got excellent agreement with our numerics and what people have published previously. So the colors correspond here. As we work along here, so the second plot is for the surface stratification, and the third is for the broad tangent profile. So if we look at the surface stratification, first of all, squares are from laboratory observations and circles are from our numerics. And you can see the colors all agree. So we've got good agreement between our numerical observations and our laboratory observations. If you just compare this panel with the first one, you can see that we've lost all these green data points. So in the surface stratification case, we didn't see any plungers. I'll explain why that is in just a second. And then if we come along to the broad tangent profile, you can see we've also lost all these yellow data points and we didn't see any collapsing waves. And again, I'll explain why that is in just a second. So this first movie I'm going to show you is a plunging example. So we've got homogeneous fluid in the top and bottom and a very sharp picnic line. This panel here is density. This one is horizontal velocity divided by wave speed. Here we're going to see vorticity overlaid with velocity vectors, and this one is vertical velocity. And I'm just going to try this. Let's see how it plays. Please let me know if there's a problem. You'll see as this wave shoals, the rear face steepens and the wave plunges over on itself. And we refer to this as a plunger. Let me just take it back and highlight some of the features more. So the rear face becomes vertical, it becomes gravitationally unstable, and the wave plunges down on itself. It's a plunging wave. If we look at the horizontal velocity in the bottom, you can see here, we see that separation of the boundary layer, and we've got the flow reversal. It gets intensified as we move up the slope, but it doesn't interfere with the wave shape itself. And I want you just to compare and contrast that with the collapsing example. So now we're looking at the surface stratification. So we've got homogeneous fluid, then a linearly stratified top layer. I'm keeping the slope steepness and the wave steepness is the same. So the only thing I've changed is the stratification. And you'll see now what happens is that the rear face goes vertical. Okay, but keep watching what happens. It looks like it wants to plunge, but in the bottom boundary, we've got this very strong flow reversal, which whips up a big vortex. And if you watch what happens, this vortex actually stops the wave plunging over on itself. And we get a collapsing wave. So what's happened here is that that separated flow in the bottom boundary layer has pushed the leeward face back upon itself. And by adding a density gradient to the top of the water column, we've essentially suppressed the plunging dynamic. Here's an example from the lab of a collapser, just to show you we get a nice agreement in the physical lab as well. So here, if I just pause it, if you watch the rear face of the wave, it's going to steepen, but keep a close eye on what goes on at the bottom. You'll see we get this big vortex generated due to boundary layer separation, which causes the wave to collapse back on itself. And we get this dense salty water being driven up the slope. Let me show you that just once more. So there's quite a lot to watch here, but if you look at the bottom, you might be able to see the flow reversal starting just now. And then there goes that big vortex and it stops this wave plunging and we get a collapsing wave instead. This figure just gives you a comparison between the numerical results and the laboratory observations. So the color scheme is horizontal velocity and the numerics were able to overlay lines of constant density. But if you just look at the two color schemes there, you can see there's really good agreement essentially between the flow features that we're seeing. Let's now have a look at the surging case. So again, we're keeping slope steepness and wave steepness fixed. But now we've got a linearly stratified water column, or a nearly linear stratified water column. And this time, what do we see? Here's the wave coming in. We get flow reversal at the bottom, but we don't get a big vortex. Instead, we get this surge of fluid, which runs up the slope, and it develops these beautiful KH billows, which mix the water as it runs up the slope. So what's happened now, we've added a density gradient in the lower layer, and that has actually suppressed boundary layer vortex formation. And our shoaling dynamics have changed, and we have a surging wave. Just want to focus on this one a little bit more because this is a new observation. So in these three panels here, I'm showing you horizontal velocity, and they're for different wave amplitudes. So we're looking at these three data points here. So I'm on a fixed slope steepness, and I'm just changing the wave steepness. So this is the smallest steepness value, and we just got a surge of fluid. As we increase the wave steepness, we get the surge having a bigger extent, and also we get these billows forming on the head of that bolus, if you like. We think these are due to shear instability. If you look here, this is the velocity field, and you can see it's oppositely signed above and below this surge. So we have a shear across there. So we think the formation of these are due to shear. Moreover, if you look at the Richardson number plots, so the Richardson number is just the buoyancy frequency squared divided by the velocity gradient squared. And a necessary but not sufficient condition for shear instability is that the Richardson number is less than a quarter. And in these three plots, you can see the corresponding Richardson number plots. And having a Richardson number less than a quarter, we don't have any observation of that in this one, which was stable. But in these, we do. Okay, so this is highly indicative that these are due to shear. We can also look at these surging boluses in a three-dimensional sense using numerics. So this lower layer is the transverse plane along this dashed line just above the bed of the slope. So you can see in this stable case, there's very little variation in the transverse direction, but we are seeing some structure when we look at these unstable ones. And this just shows this a little bit better. So we only get lateral variability after these billows form. These small scale features look a bit like lobe cleft instabilities. And also you can see that the number of billows, number of KH billows that form increase with wave steepness. And this is the same as what we saw in the 2D simulations. Okay, so I now just want to finish with the last kind of shoaling, which is fission. So here we're looking at the surface stratification. So we're looking at this data point here. And so what we've done here, sorry, let me just explain this better. So we're now changing the slope steepness. So we're looking at a very shallow slope. It doesn't look shallow the way it's plotted here, but this slope is really shallow compared to all the other ones we've just looked at. And when we make the slope shallow, this is what happens when the wave interacts. So you see that the rear face of that wave turns into a wave of elevation or a bolus of fluid at the bed. We then get a second one, a third and fourth and so on, and the wave fissions due to this shoaling process. Here's an example from the lab. Obviously in the lab, we're limited by the length of the tank, so we can't look at this in terms of the terminal phase, but we can look at the early interaction between the wave and the bed of the tank. So we're just going to concentrate on the boundary layer dynamics. And if you look closely, there's the separation, and we get these vortices forming, or these pulses of fluid. It looked like we had 1, 2, and 3, which propagate up the slope. So it looks as if there is some agreement there with the numerics. However, this is very early stage before the wave unfortunately hits off the end wall of the tank and interferes with the flow process. Here I'm just showing you a comparison between the surface stratification case and the broad stratification case for the fission. So we're comparing this data point and this data point. You can see we clearly have fission in both cases. However, there are differences. So the number of billows, for example, varies depending on the stratification type. But the other point to make is if you look at the stratification diagram, for shallow slopes, no matter what the stratification is or what the wave steepness is, we get fission in all of those cases. So here, I just want to quickly talk through some of the energetics. So if we compare the energetics for the different breaking types, so here I'm plotting the percentage of energy converted. The solid black line is the percentage of energy converted due to dissipation, and the dashed black line is the percentage of energy converted due to mixing. And if you just look at all of these plots, you can see that most energy converted goes to dissipation rather than to mixing. Okay, so the solid black line is much higher than the dashed black line. If we look at the surging and the fission cases, there's very little mixing and there's very little change in the dissipation rate when the wave interacts with the slope. So sorry, I should say the wave interacts with the slope where you see these blue crosses. So this is where the wave first interacts in this case, in this case, and this and this. So you can see the gradient of this solid line barely changes in the surging and the fission cases, whereas in the collapsing and the plunging cases, there's a clear change in the gradient of that line. So there's an increase in the dissipation rate in those cases due to shoaling. If we look at the surging broad tange case and we look at the dissipation, that's similar to the surface stratification case, but the mixing rate is much higher in this one, and that's because of the formation of KH billows in the surging broad tange case. If we look at the bed shear stress, so the blue lines here represent positive and negative bed shear stress. So this gives us an idea of potential for resuspension. If you look at the surging stratification case, the bed shear stress signal is much higher than in the broad surging case. And again, that's because in these cases, we had these KH billows on the surging wave, whereas this one, we just have a surge of fluid. So these plots suggest that the stratification type will affect sediment transport. So just to try and summarize and pull that all back together, what are our main findings? Well, we've found that the stratification form clearly affects the shoaling classification. The density gradient in the upper layer suppresses plunging dynamics, and the density gradient in the lower layer suppresses collapsing dynamics. And we found that surging boluses can support KH instabilities. Maybe the key message is that on slope steepnesses which are representative of the continental slopes, in other words, on very small slope steepnesses, then we expect to get fission regardless of the stratification form. And this work was published in JFM. It came out just in the new year. So if you'd like to know more, please do look up this reference. I'm also happy to pause at this point and take any questions before we move on to the mode 2 waves.
Okay, we have one question in the chat. Can you see the chat, or do you want me to read the question?
I'll have a quick look. Yep, see if I can get it.
Why
Why a depression type of solitary light wave where the trough is larger than the crest is considered? Unlike the open ocean, will there be possibility of elevated type solitary light waves? Okay, thank you for the question. It's a very good question. So if I can just show you quickly on here. Oh. And if I just go back to this picture. So typically what you get in the ocean is the sign of the wave. So whether it's a wave of depression or elevation depends on the location of the picnic line. So if the picnic line is located nearer the surface, then you always get a wave of depression because the wave favors going into the deeper layer. So if the picnic line is near the surface, the leading wave is a wave of depression. However, if your picnic line was nearer the bed, then the leading wave would be a wave of elevation. So actually in the ocean, the vast majority of observations, we have the picnic line nearer the surface, and these waves are waves of elevation. But you can get elevation waves if your picnic line is nearer the bed. Okay, any other questions? Okay, thank you. Oh,
Yes.
numerical simulation of flow over the slope also uses the spectral approach. Yep, so the numerical simulation is spins. So the spectral parallel incompressible Navier-Stokes solver. So the one you see here, this was the numerical method we used. And we just set up a domain that initially looks just like the lab.
Okay, thank you very much. But the question is, when you have the slope, so you have somehow modeled the boundary. So it's immersed boundary or something like that, what was used, yes?
Yeah, it's a good question. And I must admit, I don't know the finer details of the numerical code. It was Marek Statzner who implemented this for me. So my understanding is his computational domain is obviously set up to have solid boundaries, and you can specify what they are in the code, and then the code works on the flow within that domain. But I'm not sure of exactly how he sets that up.
Okay, okay. Thank you very much for the talk.
Thank you. Okay, so if I can now come on to...
There's one more question from Adele. Did you experiment elevation wave shoaling? Otherwise,
did you experiment wave shoaling? Otherwise, what would you expect? No, so good question. We haven't done that yet. We are looking at the minute at what happens when internal waves propagate under sea ice, and we're putting an ice edge there. So in some sense, that will be similar, but we've kind of flipped the domain up yet. What do I expect to see? I'm not sure yet. We do expect, I know a little bit about the boundary layer dynamics already, because I've done a bit of that on underneath internal waves of elevation. Good question. My answer is I don't know yet, sorry. Okay, so I think I'll keep going, conscious of time. I'll see if I can get through this second part of the talk fairly quickly.
Yes, thank you.
Thank you. So let's now quickly turn our attention to mode 2, internal wave shoaling. So mode 1 waves displace isopycnals in one direction only. Mode 2 displaces them in 2 directions. So you can have convex waves, like the form you see here, or concave. We're going to concentrate on convex. These are observations from the ocean, and you typically get more convex than what you do concave in the ocean, just because our stratification tends to look like this rather than this. Like mode 1 waves, they also have a surface signature attached to them. And recently, this paper by Magda and De Silva showed that if you run your SAR imagery at a higher resolution than what people have done previously, then you can pick up a lot more mode 2 observations than what we have done in the past. So this paper suggests that mode 2 waves may actually be more prevalent than what people had previously thought. This beautiful image by Emily Schroyer and others was made on the New Jersey, just off the coast of New Jersey. And you can see that the main disturbance to the picnic line takes the form of a mode 2 bulge. And then there's this oscillatory tail associated with the wave. Schroyer et al. Showed that even though the mode 2 waves have a lot less energy than mode 1 waves, the magnitude of the wave localized turbulent dissipation can be similar in both cases. So mode 2 waves may have a significant effect on eroding the picnic line, and hence on vertical fluxes of heat and nutrients in the water column. They can attain pretty big amplitudes, and such waves are known to transport mass. So here's how we generate them in the lab. So this time, the generating volume of fluid has a density of ρ2, where ρ2 is the average of the densities in the top and bottom of the water column. And we're very careful to align the center of this generating volume with the center of the picnic line. So now when you pull the gate out, this fluid wants to sit right in the center of the tank, and you get a bulge of fluid or a pulse of fluid that propagates down the tank. We're then going to look at what happens when it interacts with a linear topographic slope. And our main variables were the slope steepness and the wave amplitude. So here I'm showing a lab image and also the output from the PIV. So the color scheme is vorticity, and the vectors are given by arrows. So as this was the shallowest slope we looked at, so as the mode 2 wave propagates up the slope, you can see that it begins to flatten on the bottom. It also develops this oscillatory tail. So over the flat portion of the tank, it didn't have a tail, but as it goes up the slope, it develops one. And you can see there's a strong vorticity signal in the bottom boundary. This slope was shallow, so we weren't able to look at what happened when the picnic line intersected the slope. Here's a slightly steeper slope, and we can look at the terminal phase of shoaling in this case. So what do we see this time? So again, you see that the bottom of the wave gets shallowed. It begins to lag the front half of the wave. There's also boundary layer separation, the generation of a vortex, and this run up of fluid going up the slope. It looks like there's a little bit of a reflected wave signal here as well. And if we now increase the slope steepness once more, you'll see in this case, because the interaction time with the slope is short, the wave doesn't develop a tail. But we still see similar boundary layer characteristics. So there's the separation, the vortex generation. The wave runs up the slope again, and you can see more clearly now a reflected wave signal, which passes through the next mode 2 wave in the train. Okay, so we're able to measure this run-up length in the lab. And here I'm plotting the run-up length against slope steepness, and the different data points are for different amplitudes. So you can see here, as we increase the slope steepness, we reduce the run-up length. And that makes physical sense, because we're just saying the steeper we make that slope, the harder the wave has to work against gravity, and it's not going to get as far up the slope. If you fix the slope steepness and look at what happens when we change wave amplitude, you can see here we're saying as you increase the wave amplitude, you increase the run-up length. And again, that makes physical sense. The bigger the amplitude, the faster the wave travels and the more input momentum we have, and the higher up the slope it's going to get compared to a wave of smaller amplitude. So using this really simple physical argument, we looked at writing down an expression which balanced the net upslope momentum flux with the downslope component of the excess weight at this point here. And we came up with this scaling. And here I'm just plotting the run-up length against this scaling. K is just a constant of proportionality. And you can see that our data from the lab collapses quite nicely onto this one line, suggesting that this is a good scaling for calculating the run-up length. So we've also looked at this numerically. So here I'm just comparing the numerical simulation with the lab for the shallowest slope. Here the color scheme is density. Black represents fluid at the average density, so we can trace where that goes. And you can see that within the core of these waves, it looks as if there's some cusps of fluid. This looks like a Holmboe instability. Again, these have been talked about earlier in the week. Looks like we have some kind of asymmetric Holmboe instability going on within the core of the wave. And that's nice, as it's in good agreement with a PhD thesis that was published by Schmidt in the late 90s. And also the nice thing about the numerics is that we're able to resolve the vorticity field much more cleanly and in much more detail than what we can from the PIV. So we can see the fine scale structure and we can pick up ejection of material. Again, this is in agreement with Schmidt's thesis. Also, of course, the beauty of the numerics is that we can increase the length of the domain and look at what happens in the terminal phase of shoaling for the shallow slopes. And this is what it looks like. So you can see that the wave just degenerates into mode 1 waves of elevation. So the wave essentially runs out of steam as it goes up the slope. This is very similar to the fission process I just showed you in the mode 1 case. There was little or no boundary layer activity seen, and there was no reflected wave signal in these cases. The other thing we can do numerically is vary the Reynolds number. So in these plots here, we're just looking at a Hofmöller plot. So this is X and T. So we're looking just along the slope. The color scheme is vertical velocity. And I think this is the base case, and this is the double Reynolds number. And you can see as we double the Reynolds number, we get a stronger vertical velocity signal. So the larger we make the Reynolds number, the larger the vertical velocity. So what can we infer in that? Well, in the field, the Reynolds number is a lot higher than what we have in the lab and also in numerics. but some aspects of boundary layer flow seen for the steeper slopes in the lab could actually be replicated on the shallower slopes in the field because of this larger Reynolds number effect. So to conclude very, very quickly, for slope angles representative of the ocean, in other words, angles of 2 to 4 degrees, we've seen that the waves dissipate their energy as they show by firstly forming in a silvery tail, and secondly, evolving into mode 1 waves of elevation. The waves are effectively destroyed and there's no reflected wave signal expected. The boundary layer dynamics are negligible, but the Reynolds number analysis suggests that they could be seen in the field. Moreover, features documented here, so things like flow reversal and vortex formation have been seen in the ocean. And the bottom boundary layer dynamics are very similar to the Shoaling mode 1 case, which is exactly what we'd expect, right? Because a mode 2 wave is basically just a mode 1 wave with a hat on, but the flow beneath it, you'd expect to be the same. The shoaling characteristics are obviously very different to the mode 1 wave, so we don't see any spilling, plunging, collapsing, or surging. And again, we wouldn't expect that because of this idea of us effectively putting a hat onto the mode 1 wave. And again, this work is published in JFM, and if anyone would like to know more, please do look this up for details. I'll stop there. Thank you all very much for your attention, and I'm happy to take questions if we have time. Thank you, Philippe, and others.
Thank you very much, Magda. So we have a few minutes for questions until 11:30 French time. So floor is open to anyone who has questions, either in the chat or just unmute your mic. Well, waiting for questions. I have one, which is the waves you showed were somehow interfacial waves, right? Because they were at the interface between your unstratified layer and your stratified layer. Is that correct?
That's correct, with the exception maybe of the surface case where we have
yes.
These ones here where we had a linearly stratified layer all the way to the top.
Yeah. And so in the ocean, as we know, so what's the criteria to actually say that the wave is an interfacial wave? Is probably a criteria on the wavelength compared to the typical length of the change of density or something like that, to consider that the interface is actually an interface, or that it is continuously changing stratification. So
good question, Philippe. I honestly don't know, so I've not seen a classification of that. We tend to think of these as being interfacial waves because typically in the ocean you do tend to get this kind of structure more frequently than this, for example, or you have a clear transition to the homogeneous layer. You know yourself, if you have a linearly stratified layer, then you get waves can propagate right throughout that, so you can get wave beams and you get things like a St. Andrew's cross, whereas something like this, then you just obviously you get horizontal internal wave motion. Your question about classification, I'm not sure.
What I mean is that you have to compare, so you have a typical length of the, or typical width of the interface, vertical width of the interface, and you probably should compare that to the wavelength or something like that to decide if it's there's a question by Adele in the chat.
Okay. So you observed reflection with mode 2 waves. Is there reflection in the case of the mode 1 wave? Yeah, so it all depends on your slope steepness. Let me think, how do I best answer this? So I don't think this movie plays for long enough. Let me just quickly see. So here's an example where we get a plunging wave, and I'm just going to see if you see any reflected wave signal or if the movie stops too soon. So you can see a little bit of a reflected signal here. But to answer the question is, yes, you do get reflection, but it all depends on what is the shoaling type and how steep is this boundary. Basically, the steeper you make this boundary, the more of a reflected signal you get.
More questions? Last chance for anyone. Otherwise, we will stop here and thank Magda for your presentation. It was very nice, interesting.
Thank you. Thank you all for your attention and also for the questions. They were really, really useful. Thank you.